Okay, so it looks like it's about time for us to get ready. I was just about to say a reminder of the mask, but I notice everybody has one on, so that's super. Maybe I'll just take a moment and say thank you for wearing the mask. I recognize it's a pain, probably nobody really likes it, but I really appreciate that everybody's kind of stepping up and following MUN's policies, so super, thank you so much. Probably the only thing I wanted to mention before we get started today is the first assignment is due soon. The intent with these assignments is that you use multiple tries to get it all right. So you start working on it. After you're finished working for a little bit, you click Submit Attempt. Chances are good you're not going to finish it on the first try. That would be quite impressive if you could get 100% on your first try. Like, that would be so cool, but unexpected. So you hit Submit Quiz at the end when you're done working for a little while. You'll probably have a bunch of them not answered. That's fine. When you're ready to work on it again, you just open a new attempt and start over. At the end, when the assignment is due, it's your highest grade that gets recorded. So say you got 1 out of 10 on the first attempt and you got 10 out of 10 on the last attempt. The 10 out of 10 is what gets recorded. So there's no penalty for multiple tries, and you can try as many times as you want until you get it. Did you need a mask? I've got extras if you need it.
Sorry.
Easy to forget, hey? Okay, did anybody have any questions on how the assignments work? Not how to solve the problems right now. If you have issues, trouble with an assignment problem, we'll talk afterwards. Okay, so we did a lot of work last day. We were still talking about wave on a string. We talked about superposition is what happens when we get more than one wave in the same place at the same time. Constructive is when the waves get bigger. Destructive is when it gets smaller. We said we can have a special case of incident and reflected waves interfering to make what we call a standing wave, which is what looks like this. This is a string moving up and down, but overall the pattern looks like it's staying still. That's why we call it a standing wave. If our two constituent waves, the individual waves, if they have the same wavelength and frequency and amplitude, this is what the standing wave can be described by. So we went through that in our last class, and that's where we clued up last day. Okay, any questions before we get going on today? Looks like we're good. So we're going to work on this equation a little bit for today, or we'll get started there anyway. And our first question is going to be, where are the nodes of the standing wave? So on top here, that's a simulation from Dan Russell's website. We've got the top wave traveling to the right, the bottom wave represents the reflected wave traveling to the left, and this line right here, that represents the standing wave. So that's our wave moving over time. If you look at this wave, you see some places where the height of the wave is always 0. That's our node. So our question is asking, where are the nodes of the standing wave? So we want to find that position where y is always 0, no matter what time it is. So that's our goal in this part right here. So by where, we mean x equals what? The nodes means the height of the resultant wave, yr of x and t, equals 0 for all times. So no matter what time it is, y is equal to 0. If we think about this equation, if we want y to be equal to 0, let's think about each term. The amplitude of our standing wave, that's not 0, that's a number we could calculate. Sine of omega t, this is going to change over time, so we can't rely on this one. So we're going to get our nodes whenever sine of kx equals 0. So if we have an x value that gives us sine of kx equals 0, then we know for sure we're going to have a node, y is going to be 0 because sine of kx is 0. Okay, so let's get to solving this problem, sine of kx equals 0. Take the inverse sine of both sides. So kx is the inverse sine of 0. Is that marker big enough for everybody to see? Yeah, Okay, if at any point my handwriting gets too small, please let me know, like I can switch to a bigger pen or write bigger or something. The inverse sine of 0, if you do this on your calculator, it's going to give you one answer. It's going to say 0. But that's not the only answer. Pi is also an answer, because sine of pi is equal to 0. 2 pi is an answer. 3 pi is an answer, and so on. Okay? Again, we're back to the idea that sines and cosines are multivariate functions. So we can take the sine of a bunch of angles to get 0 for our answer. And I suppose if you wanted to get really picky, it would be plus and minus pi, plus and minus 2 pi, plus and minus 3 pi, but we're just going to stick with positive values. Okay, so now all we want to do is solve for x. Let's remember that k is our wave number, 2 pi divided by the wavelength, times x equals 0 times and pi, 2 pi, 3 pi, and so on. I'm going to divide both sides by pi, so all of my pi's are going to cancel. And then I'm going to multiply both sides by lambda over 2. So then x is equal to 0 times lambda over 2, which is 0, 1 times lambda over 2, 2 times lambda over 2, 3 times lambda over 2, and so on. So those are my positions, assuming the left side of the string is where we say x equals 0. Those are all my positions where we will have a node on the string. So this position is x equals 0. So this tells us something. We've now proved mathematically something we said when we looked at our picture, which is that every node, every 2 nodes are separated by a half a wavelength. So each of these numbers are a half wavelength apart. So there's a proof of something we said when we first looked at the picture. Okay. Questions? Yeah.
So every node, like each node happens after one cycle, basically. You can tell us.
Yeah, every half cycle.
Yeah.
Yep, absolutely. Get your nodes every half cycle. Okay, so we just found the positions of the nodes of the standing waves. You can probably guess that the next thing we're going to do is find the positions of the antinodes. So let's just look at that video again. So for our antinodes, we've got our wave going to the right, our reflected wave going to the left. We see that it oscillates up and down. Somewhere right here, we don't have the maximum displacement. It's sort of right here along this line that we get the maximum displacement. So we want to find those positions. Our antinodes are where we have the maximum distance from equilibrium. So again, where means x equals what? Antinodes are where we have the maximum motion. So on our picture, these are our antinodes. What we know about antinodes, that's where we get our constructive interference. And while I didn't write it on the last slide, the nodes are where you get the destructive interference, because that's where everything cancels out. So to get our maximum motion, our biggest value for our resultant y, so this stays the same, this changes over time. If we want our y value to get maximum motion, we want this sine of kx to be the biggest values it can be. So either a maximum or a minimum. So this would be a max and this would be a min. So sine of kx equals +1 would give us our very biggest value of y. Or sine of kx equals -1 would give us this minimum value. So those are our two extremes. So let's solve that for x. Sine kx equals plus or minus 1. Take the inverse sine of both sides. So kx is equal to, so the inverse sine of 1, if you do that on your calculator, if you're in degrees mode, you'll get 90 degrees. If you're in radians mode, you'll get pi over 2. The inverse sine of negative 1 would be negative 90 degrees. We're going to stay with positive values, so negative 90 would be the same as 270, or 3 pi over 2. Okay, and then we're at 5 pi over 2, 7 pi over 2, and so on. So all of those angles, if you hit sine of those angles with your calculator in radians mode, you'll either get +1 or -1. We want to solve for our x value, so we remember that k is 2 pi over lambda. We'll divide both sides by pi. So all those pi's cancel out. And then we'll multiply both sides by lambda over 2 to solve for our x. So x is equal to lambda over 4, 3 lambda over 4, 5 lambda over 4, 7 lambda over 4, and so on. So those are our x values where we get the antinodes. A couple of things we notice here is these are also each separated by a half of a wavelength. And they're exactly in between any two nodes. So this fits all of our observations that we made about our standing waves. It is really warm in this room again today. If people in the back want to open the windows, then please be my guest. You're always welcome to open up the windows. Okay, any questions? So now, we've looked at some general circumstances. We found our equation for the height of the wave as a function of time. I'm going to post a plug and chug example for a homework question. There's something straightforward for you to try. And next, let's zero in on standing waves on strings and those equations. So let's do a demo live, but I'm going to hit play on this simulation at the same time, just because it's a little bit hard to do live, and in case some people are watching the video. Would anybody be willing to hold one end of the slinky for me? Thank you. So we're going to use a slinky as a string, and we're going to make standing waves on the slinky, just like we had standing waves on the string. So your job is really easy. All you gotta do is hold it still. My job is a little bit harder because I gotta get the right wave. Okay, this one is the simplest wave on the string. This one is called the fundamental. If you look at this standing wave, I have a node at my end, you have a node at your end. So we've got nodes at the fixed ends and an antinode in the middle. We've got a half of a wavelength here. Okay, here it gets harder. Okay, so I kind of have a standing wave. It's not real good. And you can see this time there's 1, 2, 3, 4 antinodes. Oh, I lost it again. This is why I got the simulation playing at the same time. Okay, now I got 3 antinodes. So I can get the standing waves again. I get the same boundary conditions. We have nodes at either end, but you get more nodes in the middle as you change your standing wave. To get the standing waves, you have to have exactly the right frequency. Maybe you noticed it was really hard for me to do, and it was difficult to do because I had to shake my hand at exactly the right frequency to match the length of the slinky to get a standing wave. So we get an idea that the frequency matters. So that's where we're going to go, is we're going to figure out what frequencies will give standing waves for a specific length of an object, string or a slinky. So from a practical point of view, if you asked how did you make the standing wave on a string with 2 fixed ends, this would be familiar to guitar players. You just strum the middle of the string, Strumming in the middle sends a wave down both sides. It reflects at the two ends, comes back, so the incident and reflective waves interfere to make standing waves, which make pleasant music. So that's how you do it from a practical standpoint. From the physics standpoint, we're going to start by talking about the boundary conditions. The boundary conditions means what happens at the ends, and the thing that happens at the ends is that we have the ends are fixed and they have to be nodes. Now we can have different conditions, but we're going to start with these conditions. So let's start by saying we have a string of length L tied between two supports. I've kind of got 4 sets drawn here, so I'm going to end up drawing 4 pictures. So the length between the two supports, I'm going to call that L. As I make my standing waves, they're always going to have nodes at the ends. So I'm going to draw my node at either end because the string is tied onto that support. My first standing wave is that simplest one. You need to kind of draw both extremes. And this one is the first wave you get. This one is called the fundamental. So there's the first standing wave you could get on a string. The next standing wave has to meet the same boundary conditions. We have to have nodes, but we have to get more standing wave on the string. The way we do that is we have another node in between those two at either end. So this is my next standing wave. For the next standing wave, you change the frequency a little bit. To get more wave in there, you need another node. So we'll get 2 nodes in the middle. And then I'm only going to draw once more because my art goes downhill really fast. We put in 1 more node, and it looks like this. Okay, so that's kind of the best I can draw. So when we're developing this theory, we're going to draw the different waves that we can get on the string, and we're going to think about what are the frequencies and the wavelengths for each of those waves. Our last little bit of definitions or wording is that each of these waves are often called modes. So you might talk about the modes of standing waves on a string. You may also hear harmonics. And you might also hear resonances. Those would be the top 3. You might also hear resonant modes or resonant waves. So lots of different words. Different books use different terms. Different people in the Help Center will use different terms, but they all mean this same thing. What else? We're going to develop our theory by looking at each wave individually. That's not how real waves on a string work. Real waves on a string have a whole bunch of these different modes there at the same time, but we're going to start more simplistic rather than looking at that big overall picture at the beginning. So, standing waves on a string, not of a string, of length L. So what I've got here are just still shots from that simulation with pictures of the standing wave next to it. These pictures I took from your book, so they definitely look nicer than my pictures. Our string has length L, so that's our distance between the two supports. Our boundary conditions are that we have nodes at either end. Our first wave here is our fundamental. So that's a recap from our last slide. So now what we're going to do is let's think about the wavelength, think about the frequency, and let's see what we can figure out. For our first wave, we go from node to node. How much of a wavelength is this one? Half. So there's a half of a wavelength from node to node. So 1/2 of the first wavelength equals the length of the string. So 1/2 of the wavelength of the fundamental equals L. That tells us that lambda 1 equals 2 times L. If we wanted the frequency, we would say F1 equals wave speed divided by the wavelength, lambda 1, equals V divided by 2L. Okay. So I looked at the geometry to find the wavelength, and I used V equals F lambda to find the frequency. Give it all a subscript of 1 because this is the first wave or the fundamental wave. Okay, let's do the next one. For our next wave on the string, how much of a wavelength do we have here? That's a full wavelength. So we go from equilibrium, crest, equilibrium, trough, equilibrium. So our second wave, lambda 2, is the full length of the string. So our frequency of this wave is V divided by the wavelength of that wave equals V over L. So what we're doing now is we're writing down the wavelengths and frequencies, hoping to establish a pattern that lets us write down a description. So this is where we're going with all this. Okay, let's do the third wave. How much of a wavelength do we have this time? 1.5. We keep adding 1/2 of a wavelength. So 1 1/2 times lambda 3. You might write that as 3 over 2 lambda 3. This one equals the length of the string. 3 over 2 lambda 3 equals L. Lambda 3 equals 2L over 3. Frequency of the third wave is the wave speed divided by the wavelength, which gives us 3 times V over 2L. Okay, let's see if we can establish a pattern here. Maybe it's jumping out at you right away, maybe it's not. When I look at this, I've got lambda 1 equals 2L. Lambda 3 is 2L divided by 3. What about this one? If lambda 2 is equal to L, it's the same as 2L over 2. So for my wavelengths, I see I've got 2L over 1. You can always divide by 1. 2L over 2, 2L over 3. There's my pattern for the wavelength. So in general, for waves on a string, which are fixed at both ends, my wavelength of any mode or harmonic or resonance, lambda n, is equal to 2L divided by the number n, where n is an integer. 1, 2, 3, and so on. This n has a specific name, and this n is called the harmonic number. So n tells you which mode it is. Some books, I can't remember if yours does it or not, it simply defines n as the number of antinodes. I don't think that's a great way to do it because we're going to get into lots of different things. I think it's better to evaluate what your pictures look like and which mode it is. So n equals 1 means fundamental, n equals 2 means the next one, n equals 3 is the next one. So different ways to think about it. So there's our wavelengths. For our frequencies, we have a similar kind of pattern. We've got V over 2L. Our next one is V over L. That's the same as 2V over 2L. Then we've got 3V over 2L. So for our frequencies, the frequency of any harmonic is equal to n times V divided by 2L. What we might notice in this expression right here is that V over 2L is our fundamental frequency. So we could also say, or Fn is equal to n times the fundamental frequency. It's the same expression, just two different ways to write it down. Where n is the same thing, 1, 2, 3, 4, 5, and so on, all the positive integers. Any questions here? Okay, so I'm just going to add at this point that we often use this, and this is more of a tip in problem solving than anything else. Often use that with V is the square root of tension divided by mass per unit length. So you'll frequently see both those equations in the same problem. I'll issue you a challenge for something to think about, and we will eventually get through this sort of method, is what if you had a string, but not exactly a string, maybe something thin and flexible, but instead of having both ends fixed, what if you had one end free? Okay, so you just kind of waved it up and down like this. If you do different frequencies, you can still get those antinodes and nodes. Could you apply this sort of analysis to this sort of a setup to figure out your wavelengths and your frequencies? So there's something you might want to try just to see if you're a little bit on top of this material. Okay, any questions? All right, let's go to an example. So in our example, why don't we draw it as we go? We have a 200-gram mass. It's hanging from a long string draped over a pulley and attached to a frequency generator. So this is like the setup we had in class. Here's our frequency generator. There's a table. Here's a string going over a pulley, and hanging down at this end is some mass. Okay, so there's a picture of what's happening. Let's get a little information on here. Let's call our mass capital M. That capital M is 0.200 kilograms. Right off the bat, I'm just going to switch to SI units. I know I've got newtons and all that stuff in here, so you're best off working in kilograms and meters. My frequency generator is variable. Its lowest setting is 60, its highest setting is 120. So 60 hertz is less than or equal to the frequency, which is less than or equal to 120 hertz. So those are the only values of frequency we can get. The mass per unit length of the string, it's got a symbol of mu. It's 1.51 grams per meter, so 1.51 times 10 to the minus 3 kilograms per meter. So there's our given information. The length of the string between the frequency generator and the pulley is 90 centimeters. I'm going to call that L. L equals 0.90 meters. So just like we had in our classroom setup, it's this length of string where we're going to see the standing waves. We're not going to get any action down here. The point of this part down here is just to provide tension in the string. So part A, which frequencies of the generator will give us standing waves on that string? So we want to figure out what are the frequencies that are going to give us a standing wave. So let's write down our expression for frequency. So the frequency of any harmonic, and we don't know what n values we're going to have just yet, so we don't know that, let's just put in an n, is equal to n times v over 2l, where n is my harmonic number. Doing this equation is great. I know I get different values of n. I know my L is 0.9 meters. I don't know my v. So let's pause and see if we can figure out v before we can carry on with this equation. So I know that wave speed on a string v is the square root of the tension divided by the mass per unit length. To carry on with this problem, I need to figure out the tension in the string. It is not good enough for you to write down F equals mg. I'll put a big X through that on a test. I'll mark it wrong and I'll give you 0 for it. Because tension is not equal to mg, weight is equal to mg. So you have to start with a free body diagram. So you draw your mass. We've got the tension holds it up. We've got the weight pulls down on it. For weight, I'll call that F with a G on it, force due to gravity. So that's what your book uses. I'll apply Newton's second law. Sum of the forces in the y direction is mass times acceleration in the y. So I've got my tension up minus my weight down. That's where mg comes in. Equals 0. The acceleration is 0 because this mass is not moving up or down. So now we see that the magnitude of the tension is equal to the magnitude of the weight, m times g. So you do have to go through this process. It's not okay to skip the steps and just write down tension equals mg. If you're a numbers kind of person, you'll plug in your m and your g, and you'll find that that tension is 1.962 newtons. If you're a symbols kind of person, you'll leave it at mg till you get to the very end where you're trying to do a calculation. Either is fine. So we've got our tension. Now let's calculate our wave speed. And our wave speed turns out to be 36 meters per second. Okay, now we've got V and we've got L, we can think about what waves we're gonna get on this string. Any questions? So I'll start with my equation. Right off the bat, looking at this, I kind of have an idea of what n is going to be. That probably comes from doing physics for 30 years. If you don't know the n values right off the bat, and you probably won't, because I guess nobody here has been doing physics for 30 years. So why don't we start at the beginning? Let's try n equals 1 and see if that's going to give us an answer we're happy with. So I'll try n equals 1. So my F1, the fundamental wave that I could have on this string, would be 1 times v over 2L equals 1 times 36 meters per second divided by 2 times 0.9 meters to get a frequency of 20 hertz. If our frequency generator could go that low, this would be the first standing wave, but our frequency generator doesn't go that low. It stops when we get down as far as 60, so we got to put an X through this. Looking at this one, we might have an idea that the n equals 2 mode is not going to work either. So if we use n equals 2, the frequency of the second mode would be 2 times the fundamental frequency, 40 hertz. That one doesn't work either, because our lowest is only 60. So now we get to n equals 3. F3 equals 3 times F1 equals 60 hertz. So there's the lowest frequency standing wave we can have on that string. It's the n equals 3 mode. Then let's keep going until we get to frequency equals 120. So these are the allowed waves. Or the allowed modes or the allowed harmonics. So these are the ones we're going to get because these are the frequencies we can set our generator to. Okay, so there's part A done. Part B says sketch the first allowed standing wave and say what the mode is. Well, for part B, we've got half of the work done. So for part B, n equals 3 is the first mode. And our n equals 3 wave will have 1.5 wavelengths on that string. So I'm just going to draw it right on top of my string. So there's my picture for part B. Here we might remember that we are talking about linear waves. So really this amplitude is very tiny, like it's not very big at all. I've exaggerated it because it wouldn't look like much if I drew it with a teeny tiny amplitude. But in the real world, this is not going to be a great big amplitude, it's just going to be a small amplitude. Okay, questions? Oh, still doing good. Let's ask a slightly theoretical question, slightly practical question. Yeah?
How do you know that there was only going to be 2 nodes besides the ends?
So how did I know to draw this wave?
Yeah.
That's such a good question, and there's a few different answers. So my first answer is because I just drew it a minute ago. Okay, so that's my first answer. Seriously, right? It sounds funny, but it's true. Is we just drew this on the previous slide, that this was the n equals 3 mode. You may not always remember that quite so quickly. So if this were a test situation, and you didn't have that at your fingertips, you would probably start at the beginning and start to draw them. So you would know that n equals 1 is the fundamental, and it looks like this. Your next wave needs one more node in the middle, looks like this. Your next wave needs one more node. So that's the way I would suggest to do it. And some people remember these things really well. Like, some people are rememberers, some people are figure it out. Everybody's brain works a little bit different. If you're one who prefers to figure it out, you'll probably start from n equals 1 and keeps going. If you're somebody who just remembers these images really well, you'll probably jump right in with the picture. So whatever works for you.
So not a node should always be one more than whatever the node is, so if it's n equals 2, it should be 3 nodes?
One could do that, yes. Yeah.
So number of n equals the number of antinodes, would there ever be a situation that we would see that would not be the case?
Off the top of my head, I'm not sure if it's true when you have one fixed end and one free end, or if both ends are free. Yeah. So off the top of my head, I can't say that that's always true.
Okay.
Yeah. Okay. Great questions. So now let's see. So, way back when, in the old days, when our family got our first microwave, it didn't have a rotating turntable, like you just put it in, it stayed still. I just assume probably everybody has a microwave. Does everybody have a microwave that the table rotates? Does anybody not have one? No, okay, so that would be really old. I'd be surprised if you could ever get one. So the ones I had didn't have a rotation. The ones you have do have a rotation. Why?
There are microwaves,
Oh, sorry.
same microwave, the waves are too big, they have to spin so it covers.
Spin so it covers. Okay, anybody want to kind of pitch in, add anything to that?
Yeah, you'll get nodes in the middle so that the water molecules don't oscillate and actually eat the food, so you have to turn it so there's never a node in one spot of the food.
Okay, so node in the middle. Anything else?
To warm it up evenly.
Warm it up evenly. Okay, so everybody's thinking about all the right stuff. So a microwave emits microwaves. These are electromagnetic waves. And it does create a standing wave inside of the cavity of the microwave. So you get a node at either end inside your microwave. And you get standing waves that look something like this. So yes, you are 100% correct. When you have these standing waves, at the antinodes, that's where you're getting the biggest oscillation. So that's where stuff is going to get the hottest. So we get the very most right there. Right here, that's where you have the nodes. That's where stuff stays raw or cold, depending on whether you're cooking or warming it up. Something you can do, and this would be really fun to try, I think it's really cool, is if you look at your microwave, if you turn it around and you look at the sticker on the back, it's going to give you the frequency of your microwave oven. So it'll tell you in hertz or megahertz or gigahertz, whatever it is. So it's going to give you the frequency. If you put something in your microwave, and I'm thinking just a plate of raw egg, like you scramble it up a little bit, if you put that in your microwave, take the turntable out, don't let it rotate, put it in and just cook it for a little while. You should see hot spots in your eggs and you should see raw spots in your eggs. Your two raw spots would be a node to node distance. You could figure out the wavelength. Okay, so you could use your plate of eggs cooked for a little while to find the wavelength inside your microwave. You could look at the sticker on the back to find the frequency, and you can calculate the speed of an EM wave. You should get 3 times 10 to the 8 meters per second. So I invite everybody to try this at home. Please let me know how it goes, because I think that's kind of cool physics you can't try at home. Questions? Anybody think they might try it? Okay. Some people might. Okay. Excellent. So let's see if we can get through one more example before we have to quit today. We still got 10 minutes left. I took this one right out of your textbook. It's a pretty good example. It's got kind of some different stuff in it. So in an attempt to get your name in the Guinness World Book of Records, you build a bass, not a musician, I don't even know how to pronounce it. Is it a viol? A musician? Vol? Yeah. A big instrument, a big stringed instrument, with strings of length 5 meters. So this is really big, 5 meters, about 15 feet, between 2 fixed points. One string, the linear mass density is 40 grams per meter, and it has a 20 hertz fundamental frequency. And we want to find some different stuff. So I'm going to write down the length of the string, 5 meters. I'm going to write down the mass per unit length, but I'm going to convert that to kilograms per meter. And I know something about the fundamental frequency. It equals 20 hertz. And while I'm thinking about the fundamental frequency, I'm just going to go ahead and draw it because I'm thinking about it. Okay, so there's my given information. The first thing I'm asked to find is the tension of the string. So let's think about how we're going to find tension. If we want to find tension, let's think of the only equation we have with tension in it. And that's that wave speed V is equal to the square root of the tension divided by the mass per unit length. Okay, so there's our only equation with tension. We've got to use this if we want to find tension. Square both sides, multiply by mu, and we get V squared times mu is equal to the tension. So I want the tension F. I know mu. The next part to be able to solve this problem, I need to figure out the wave speed. So let's see if I can find the wave speed. Well, I know that my fundamental frequency F1 is equal to V divided by 2L. So my wave speed V is my fundamental frequency times 2 times L. So my fundamental frequency is 20 hertz times 2 times my 5 meters. My wave speed V is equal to 200 meters per second. So there's the wave speed on that string. We can put that into our equation for the tension. Tension is equal to V squared times mu, 200 meters per second squared times 40 times 10 to the minus 3 kilograms per meter to get a tension of 1,600 newtons. So there's the tension in that string. Any questions? Okay. Part B, what is the frequency and the wavelength of the n equals 2 harmonic? So part B, n equals 2. As soon as I think about n equals 2, I'm going to go ahead and draw that wave. If I want to find the wavelength, I think I'm going to look at that. I'm going to recognize that I have a full wavelength on the string. So my wavelength is equal to my length of my string, which is 5 meters. And that was my second wavelength. For my frequency, F2, there's different ways to do it. You could use F as V over lambda. You could do F is equal to 2 times V over 2L. So the harmonic number 2 times V over 2L. Or you could say it's 2 times the fundamental frequency. So lots of different ways. Whichever of those 3 waves that you picked would all be correct. They'd all give the same answer. And that equals to 40 hertz. Okay, any questions there? No, still good. So our last bit, and this is going to be a very nice segue into our next chapter, says what is the frequency, what are the frequency and the wavelength of the sound waves produced in the air when the string is vibrating at its fundamental frequency? So now we're talking about a link between making a wave on a string to a wave in air. I think this is a really interesting idea, and this leads us into talking about how sound is a wave and how it works in air. So the string goes up and down. The string is going up and down in air, so it bumps into the air molecules. This string goes up and down 20 times every second. So it bumps the air molecules 20 times every second. It makes the air molecules vibrate 20 times every second. So the frequency in air is equal to the frequency of the string. Does that make sense as an idea? Okay, super. For our wavelength in air, this one is going to be different. We're not going to have the same wavelength as the string on the string as we will in air. So our wavelength is going to be the wave speed divided by the frequency. The speed of sound in air is typically about 344 meters per second. Divided by the frequency of 20 hertz would give us 17.2 meters. And actually that gives us enough time to start our first slide of the next chapter. So let's just do that. Any questions here before we move on? Yep.
Whenever we're told the speed of the sound in air in a question and the number is not given, would we have to assume that it's 344 meters per second?
Yeah,
Or would it always
typically.
be given?
No, you'd either be given enough information to calculate it, or you assume 344, or I'd put it on the formula sheet. So, what is a sound wave? And we're going to study sound waves for a while. And one of the reasons we study sound waves is because we learn a lot through hearing. So we listen to people speak, we listen to music, we listen to our environment. So a lot of our world information comes in through hearing, so that's a good reason to study it. For our definition of a sound wave, it's a longitudinal wave, so like when we compress those coils on a slinky and let it go. Sound waves travel through gas, liquids, and solids. It does need a medium, so it can't travel in a vacuum, but it does travel through solids. And what happens is when those vibrations get to our eardrums, the eardrum vibrates, transmits it to a signal which your brain perceives as sound. So we get a real physics biology crossover there, so the same thing happens at the same time. So let's get an idea of how sound works. So if you have your cell phones, I guess everybody has their cell phones, first thing you can do is turn your volume up. So get your volume nice and loud. Everybody should be playing along here. Open up a music app, whatever you use to listen to music. Oh, I'm so slow getting mine open. No doubt you are all faster than I am. So find a song. Okay, I'm going to play the first song on my list. So turn your music on. I can wait all day. And put your hand on top of your phone and just feel it. Okay, I just realized mine wasn't the clean version. Okay, so when you had your music on and you were touching it, did you feel it vibrating? Okay, that's where the sound comes from. This is a little speaker I have. I popped the top off. If you have speakers at home, you're welcome to do it. There's a diaphragm inside, so your music is transmitted to an electronic signal, which goes through the circuitry, and it makes this diaphragm vibrate in and out. That vibration in and out is the same thing as that string vibrating in and out. I'm just going to play this one so we get a visual image of it. So this is from a PhET simulation. That diaphragm vibrates, squishes the molecule, and the squish travels. So that squishing of air molecules is a sound wave. Okay, now we're up to full time, so we'll quit there, and then we're back on Wednesday.